There's something deeply satisfying about watching skilled craftsmen work with fire and steel, just like the blacksmiths of old. Here at the Czech Republic Forging Association, they're keeping those timeless traditions alive while embracing modern precision. What we're witnessing is a fascinating blend of heritage and technology. The Czech Republic has been a center of metalworking excellence for centuries, and these forging shops carry on that proud legacy. The process begins with carefully selected steel billets, heated in gas-fired furnaces to precisely 200 degrees Celsius. That's about 200 degrees Fahrenheit for us. At this temperature, the steel glows a brilliant orange red and becomes malleable enough to shape. Watch as the forge master positions the heated billet under the power hammer. These aren't your grandfather's hand hammers. These are hydraulic giants capable of delivering 5,000 pounds of force with computer-controlled precision. Yet the skill required is every bit as demanding as it was 100 years ago. The operator must read the steel, feeling how it moves, knowing exactly when to strike and when to rotate the piece. Now comes something particularly interesting: the marking process. Each forged component receives its identification stamp while still hot. This isn't just bureaucracy, it's a matter of pride and accountability. The association uses a specialized pneumatic marking system that stamps each piece with a unique identifier, the shop number, and the date code. This system ensures traceability. If this part ends up in an aircraft engine or a ship's propulsion system 30 years from now, someone can trace it back to this exact moment, this exact forge. The beauty here is that they're maintaining the soul of traditional forging while meeting modern aerospace and automotive standards. It's craftsmanship you can depend on. Now, if you remember the machine shops of the 70s and 80s, you'll appreciate just how revolutionary this technology is. Back then, you'd turn a part on a lathe, then move it to a milling machine, losing precious accuracy with each handling. Those days are gone. What you're seeing here is SolidCAM software controlling a modern turn mill machining center. It's like having an entire machine shop contained in one magnificent piece of equipment. These multifunction CNC machines feature what's called a C-axis, a Y-axis, and live tooling capability. Let me break that down in plain English. The C-axis allows the main spindle to rotate to any precise angle and hold it there, not just spin continuously. The Y-axis adds up and down movement to the traditional left-right motion. Live tooling means the machine can hold rotating cutting tools, like end mills and drills, not just stationary turning tools. Put it all together, and you've got a machine that can perform both turning operations, like making a shaft, and milling operations, like cutting slots or drilling holes, all in one setup. Here's why that matters. When you clamp a workpiece once and complete all operations without moving it, you maintain incredible accuracy. We're talking tolerances of plus or minus 0.02 of an inch consistently. In the old days, achieving that required master machinists and multiple setups. The SolidCAM software is the brains behind this operation. The programmer creates a 3D model of the finished part, and SolidCAM automatically generates the tool paths, the exact movements the machine will follow. It optimizes cutting speeds, determines the best sequence of operations, and even simulates the entire job before cutting the first chip. Watch how smoothly it transitions from turning the outside diameter to milling those cross holes. No human intervention, no repositioning, no loss of precision. This is modern manufacturing at its finest, combining computer intelligence with mechanical precision to produce complex parts that would have taken days in just a few hours. Here's a machine that would have seemed like pure science fiction to the metalworkers of yesteryear. the Occupok AHS 30 to 150 plate rolling machine. This Turkish-built beauty can take a flat steel plate and roll it into a perfect cylinder with remarkable precision. The AHS 30 to 150 features a 3-roll pyramid configuration. That's 1 bottom roll and 2 top rolls that can be adjusted hydraulically. It handles plates up to 150 millimeters thick and 3 meters wide. That's nearly 6 inches thick and almost 10 feet wide for those of us who grew up with imperial measurements. Watch how the operator feeds the plate through. The bottom roll is powered and pulls the material through, while the 2 top rolls apply downward pressure, gradually bending the plate. The beauty is in the control system. Hydraulic positioning accurate to within a half millimeter ensures consistent curvature along the entire length. What's particularly impressive is the pre-bending capability. See how it eliminates that flat spot at the leading edge? The top rolls can shift position to bend the very ends, something that required separate equipment in the past. This machine is producing cylinders for industrial tanks, pressure vessels, and large diameter piping, the backbone of modern industry. Now this is something special, a fully automated stator production line from China's Nide Corporation. If you've ever wondered how electric motors are made today, you're about to get a front row seat to some impressive robotics. For those who might not know, a stator is the stationary part of an electric motor. It's the outer ring that contains copper wire coils. These coils create the magnetic field that makes the motor spin. Every electric motor has one, from the tiny fan in your computer to the massive motors that power industrial equipment. This production line begins with stator core laminations, thin sheets of electrical steel stacked together. A robotic arm picks up each core with vacuum grippers and positions it onto the winding station with millimeter precision. Remember when this was done by hand? Workers would spend hours carefully winding copper wire around each tooth of the stator core. Now watch this automated winding head. It's programmed to wrap copper wire around each stator slot at precisely the right tension. Too loose and the motor loses efficiency. Too tight and you risk damaging the wire's insulation. The machine completes in 2 minutes what would take a skilled worker 30 minutes. Next comes the insertion process. Another robot transfers the wound stator to the insertion station, where specialized needles push the coil leads into their designated slots. The precision here is remarkable. We're talking about inserting multiple wire ends into slots just a few millimeters wide without damaging the delicate insulation coating. The lacing robot is particularly fascinating. It weaves a protective cord through the coil ends, securing everything in place and preventing vibration damage during motor operation. This used to be purely handwork requiring years of experience to master. Finally, the testing station. Every single stator gets checked for electrical continuity, insulation resistance, and winding accuracy. Any defect triggers an automatic rejection. The accepted stators move to the varnish dipping station, a protective coating that seals out moisture and provides additional electrical insulation. This entire line produces a finished stator every 45 seconds. That's efficiency our fathers could only dream about. Folks, what you're looking at here is something truly extraordinary. A 12.5-meter-long crankshaft being precision ground on a DB12500 CNC crankshaft grinder. That's over 41 feet long. This isn't for your car's engine. This is the beating heart of a massive marine diesel or a power generation plant. Crankshafts like this power the great ocean-going container ships and oil tankers or generate electricity for entire cities at thermal power plants. These engines can stand 3 stories tall and produce over 100,000 horsepower. Just imagine the forces involved. The DB12500 is a marvel of precision engineering. It's grinding the main bearing journals and crank pins to tolerances of just 5 microns. That's 5/1000ths of a millimeter, or about 2/10,000ths of an inch. On a shaft this massive, achieving that kind of accuracy is genuinely remarkable. Watch how the grinding wheel traverses along the journal. It's not just spinning and touching the metal randomly. The CNC control system is adjusting feed rates, grinding wheel speed, and depth of cut thousands of times per second based on real-time measurements. Temperature sensors monitor heat buildup because thermal expansion could throw off those tight tolerances. The grinding process removes work-hardened material from the forging process and creates the mirror-smooth surface finish necessary for these highly loaded bearing surfaces. Between each grinding pass, the machine uses a sophisticated measuring probe to check dimensions. If it detects any deviation, it automatically compensates on the next pass. This closed-loop feedback system is what makes modern precision possible on such an enormous scale.